2014, the Cambridge group, the John Dyer and others, they have made the Guinness record trapped field at 17.6 Tesla in a stack of the two silver-doped gallium barium couple valves. So that people may expect what is the performance of this kind of valve to be applied to the rotating machine. The problem is the magnetization. I proceed to the materials and the magnetization concept part. And then to obtain intensified flux trapping, we need to magnetize the bulbs below TC thanks to flux spinning mechanism. And then to do this, it is relatively easy to cooling the material from room temperature to below TC under the external static magnetic field, for which we employ the superconducting magnet. But however, it is necessary to prepare the designed superconducting magnet. So we may design a specialized scale and also that special order of the winding. So it may be, the cost should be expensive. So for simplicity, the pulsed field magnetization technique, PFM, is widely known and has been intensively studied. In this, we may momentarily apply an intensified magnetic field to the bulk HTS even after we install them inside the designed machine. Of course, there are many works that have been done in the basic level in the laboratory. The target is how do we magnetize the intensified flux trapping as much as possible. So these are, what is problematic is the heat generation due to mobile flux during magnetization, because we apply the magnetic field momentarily, so that the intensified flux that may be mobile inside the bulb, which causes considerable heat. So in our group, the Professor Ida now in the ThermSat has a challenge to solve the optimization of the waveform of the pulse magnetic field, because usually by using the conventional LCR circuit, we may get this kind of the shape of the pulse as a function of time. But this slide shows that how we apply pulsed current as well as the pulsed magnetic field. The Professor Ida and his group, of course, they have first constructed this kind of the magnetization coil, and then they try to magnetize. This is just the well-known circuit. And then, but he noticed the optimization of the waveform of the pulse. And then the first step that he tried to just do the change of the DC current control only. But secondly, that he tried to the feedback control with the magnetic penetration. We put the Hall sensor the center of the top center of the bulk surface. And then we may watch this kind of magnetic field. Then this value should be feedback of the PC, and then we may control the magnetic flux density by way of the modulation of the applied current, the field control. So for example, I enhance the graph again, and then this is the discharge current. This is just conventional one. But if we apply the waveform control pulse, we may get this kind of modulated wave. We may avoid the peak pulse intensity thanks to the modulation. Especially they have developed the chopping, the alternation of this circuit. Immediately they apply to this kind of things. And then the figure shows the magnetic flux at the top center position can be trapped. This one, this is the green curve as a function of time. The vertical is the magnetic flux density. The can be trapped as the remnant flux by way of the feedback control of the duty ratio with the center field during the single pulse wave period. The duty ratio means that more or less the alternate chopping, this is 1 millisecond, the periodicity. But during the period, they control the onset time of the energization or of energy, so that they can control, so that they define the duty ratio, energization time divided by the on period around this 1 millisecond. So it was the 2016, and they have reached to the mostly the 96% of the trapped magnetic flux density by field cooling by way of this the new technique of the pulse field magnetization. This graph exhibits the success record. This is the broken line of the red, and others, the data is just fixed duty ratio data or just conventional one. This is quite general circuit usage by way of the construction of only LCR. This is just transient response. This is quite well known. So this correction of the magnetic field as a function of time with different fixed duty ratio and the feedback control by using the center field density, mostly that we reached the 1.63 Tesla at liquid nitrogen temperature, right? So this is quite a recent result, reported by the Anton Kohns in the UCAS, and then now submitted to the IEEE task. These figures seems to be complicated, but indicate that we obtained the mostly satisfactory trapped flux in the top center. This case is the growth sector, and this is the growth sector boundary, and this is the top center position. That we put the Hall sensor for each position, and then we applied the variety of ways. Of course, it includes the waveform control pulse magnetization with the feedback. So finally, we compare the trapped flux for the conventional pulse PFM, and this is conventional PFM, for example, in the top part case, and the fixed duty ratio, more or less the 40% or the 50%, and also that only fixed duty ratio, this ratio without the feedback control, but we apply the feedback control, and then during the process, we have changed the target magnetic field in the control circuit. Just the change of the target field, which means that allow us to change of the maximum current flowing in the magnetization coil. So a little bit complicated, but thanks to this kind of procedure, we reach to the very good result. And then you can see that WCPM and the waveform control, the pulse magnetization negative feedback, this is more or less close to the 3 Tesla at 50K. So that at this moment that we are very satisfied with this kind of progress, and then we could reach to the more or less the 3 Tesla at 50K by way of this kind of progress. But the second concept for the magnetization is that we should focus on the off-axis magnetization, because most of the results, the single grain bulk high temperature superconductor, of course, exhibit the intensified flux trapping performance upon field cooling magnetization. But the world record is also 70.6 Tesla, as we have seen. But however, the majority of the magnetization studies, the focus on the magnetization along the crystallographic C-axis. Z-axis is the perpendicular to the top surface usually. And in the present study, the Dr. Ricci in our laboratory, he tried to clarify the flux trapping performance and the field-cooled magnetization using an off-axis magnetic field with respect to the Z-axis. Because we can imagine that in the near future design, in the variety types of the rotating machine, we would like to put the bulk magnet. Of course, we would like to modify the shape, or maybe sometimes is a tricky geometry which should be required, so that this kind of result should be very important. And then the result shows that the trapped flux is almost polarized along the applied field as expected. This tendency that can be exhibited this kind of graph. We have plot the maximum trapped flux and also that integrated trapped flux, the other function of the inclination angle. I say that the off-axis angle theta. And then this tendency remains up to high off-axis angle theta around 60 degrees. And it is worth mentioning that with theta of 30 degrees, the maximum trapped flux component B parallel match, this is significantly remain the more than 96% of the 1.6 Tesla. So that we have something freedom to put the bulk magnet inside the machine. So meanwhile, the angular dependence of the Z-axis parallel component exhibits that observed flux density is higher than that of the expected from 1.6 cosine theta curve. So that we think that it is highly emphasized that this off-axis magnetization with a finite inclination angle is quite useful for introducing into the design of HTS application. Okay, so that we may proceed to the machine design concept. And firstly, I would like to review the axial flux machine. This is the cross-sectional view of our test prototype machine and the specification, the 10 kilowatt, 720 RPM. And then this is just a schematic drawing, but we have put the induction motor as a prime mover and connected to the excess bulk generator that we operated this rotating machine and generator, and then we got a variety of parameters during the several years of test. And field pole bulks on the rotor are cooled down by way of the closed cycle sum siphon, mainly by using neon gas, and the lowest temperature is 40 Kelvin. And armature copper winding, this is just conventional copper winding and the concentration winding, and then cool down by a flow of liquid nitrogen. And we may apply the pulsed current to magnetize the bulk. But this is the more or less the analogy to the basic laboratory experiment, which has been done in many years in the many laboratories. So this kind of the operation test, it was done successfully running and then already reported by Dr. Matsuzaki and Dr. Watasaki, so that everything is work very well. And then important device is the cryo-rotary joint. You can find that this one is the commercial one produced by some Japanese company, distributed in more than 10 years ago, but it's very too large. And then we have minimized the size, and together with the good thermal insulation, we have designed the mechanically and as much as possible that we have the compacted design. So it works very well. And then we have success to the development of the simple, compact, and effective cooling the performance. And then coupling is very good. And of course, we apply the magnetic fluid. So if we enhance the rotating frequency, we can observe considerable heat loss, which is low, but we may have visibility to this kind of increasing as a function of rotating speed. But it is coming from the heating of the magnetic fluid. So we cannot avoid these kind of things, but it should be allowable to our performance expectation. And this is just to attach the configuration between the rotating machine and the cryocoolant part. So specification can be seen here, and then we already applied the test of the helium and the mixing helium and the neon gas and the nitrogen. So it works no problem, and so we believe that this kind of attachment and should be the very important device to be included in the future the machine. And of course, the cooling is a very important issue. To achieve an optimal performance of this field for the magnet in ship propulsion motors, it is crucial to regulate the operation temperature under 40 K, for example. And a simple and reliable cooling system is necessary. The thermosiphon, we may abbreviate TS sometimes, but the thermosiphon cooling is highly suitable and very nice the performance. And then structure is very simple. Dr. Yamaguchi has performed a very detailed experiment and published his PhD thesis in the Journal of Thermal Sciences. And then he got to the boiling curve, which can be applied to the variety of the system design. So I think that this paper should be the good difference to the design that another types of the machine.
The Professor Izumi, it remains 3 minutes for your talk.
Okay, thank you very much.
Okay.
And radial flux machine has been operated successfully, and we have published the stability model and the property of this kind of machine, 30 kilowatt and 190 RPM. And then this is similar to the axial flux, but you can find the radial flux machine like this. And then we may apply just to the conventional, the armature, and then just the retrofit type, and just we only design that rotor with 4 pole, and then single pole can be composed with the 15 the platelet of the bulk. And then this unit can be easily applied to large scale machine for ship propulsion, for example, 4 megawatt. So in summary of the POC proof of concept of the high power density machine, we successfully designed the prototype of the axial flux machine and also that radial flux machine. Both machine, of course, we applied the bulk, the gallium 123. So these POC machine prototype, radial flux machine, especially the recorded as follows. The thermosiphon is working very well, and the magnetized, the bulk field for up to 3 Tesla at this moment. 5 Tesla is possible. The magnetized by the field cooling system in this case, and no demagnetization and no field degradation during the more than 300 hours testing and the load during. And also 10 months operation of cryogenics is very well. And then even though we have experienced a 10 minutes blackout, but after that, the motor and generator works very well without any drastic change of the performance of the bulk. So we have published everything results in this SSR this year. And then we believe that the 4 megawatt motor concept design, it should be a very feasible one. And also that the application of the concept that we now approaching to the marine current turbine generator, so that according to design of the contra rotating marine current turbine generator, we fit to the bulk the field pole, that we may apply both sides to the outer and the inner armature. So now we are approaching to the realization of the prototype of this kind of wind turbine, not current turbine generator, this one. Okay, so the torque consistency is also calculated between the input mechanical torque coming from the turbine and with the tide flow the 2.5 meter per second to the electromagnetic torque for the generator side. So that in conclusion, the design of high power density HTS machine by using bulk, so this kind of the design and the POC test has been successfully carried out at this moment. That may be applied to the electric aircraft, but for us, no remarkable project exists in a site. And the magnetization should be possible to the impulse field magnetization and also that the field magnetization up to 5 Tesla. It is no problem, I think. And POC for large-scale machine design should be expected. And then we believe normal modeling simulation, but practice together with cryogenic or cryomechanical engineering aspect is very, very important. So we should do and we should approach to the realization of the machine operation for many, many tests for practical application. So this is finally, I would like to acknowledge Mr. Clement Bokew and Brice, Dr. Brice and Suzuki and Dr. Ingrid Bretton and Roberto Chin from ABB and Dr. Morita-san and Teshima-san from Nippon Steel. Okay, thank you very much for your attention.
Thank you, Professor Izumi. Is there any question in the audience? So one question from Min Zhang. So Min, are you here? Can you ask your question, or it's just right on here? So she wants to ask how to prevent the cracking and degradation of the bulk during motor operation. Did you experience some crack, Professor Izumi?
Yes. To our knowledge and to our experience, that we have the experience, probably the maximum degradation of the total flux of the bulk during the whole operation is less than 1%. So that we have done a synchronous operation in principle, so that so far we have never experienced a drastic degradation, and we never experienced the broken, and we never experienced the remarkable degradation and decreasing performance the past years. So we believe very much for the performance of the bulk and survivability. Survivability, I think, is quite enough.
Okay, thank you. I have one question. You mentioned the control pulse field magnetization and the energy applied for magnetize the bulk. What about the dissipation in the coil? Did you experience more dissipation or heating of the magnetizing coil in the case of longer pulse?
Of course, we have done something cooling by using the liquid nitrogen or other ways to cool down the magnetization coil, so that just only for heating that we don't have any big problem. Okay. But of course, because of the temperature change, that we may experience a change of the impedance.
Okay. Thank you again, Professor Izumi.
Thank you very much for your attention.
Thank you.